Greetings to you. Welcome back to Physics with Ben. This is a continuation of video 1 on this topic, video 2 on this topic. So this is the third video on this topic. In today's video, we want to concentrate on change of states and latent heat. In the previous video, we looked at the definition of heat energy, specific heat capacity, thermal capacity. We looked at how the methods used in determining the specific heat capacity of a substance. We looked at the method of mixtures and also the electrical method. Kindly visit those videos and watch them before you come back to this video. Previously in your SS1 or your year 9, you have been told that addition of heat energy into a system will cause some changes in that system. We talked about change in temperature. We also talked about expansivity of the body, that is expansion of the body. We also talked about change of states. In expansion of the body, we looked at linear expansivity, volume expansivity, cubic expansivity, apparent cubic, and re-expansivity. Kindly visit my video on linear expansivity. I have done a detailed video on that topic so that you understand what I'm talking about. But we were unable to produce a video on change of states. And so in today's video, we want to comprehensively look at this topic. By the way, what do you mean by change of states? I define change of state this way. Change of states is a physical process whereby matter changes from one form to another due to the addition or removal of heat energy. In other words, I am trying to say that change of state is a reversible physical process. And so I present to you another definition. Change of state is a reversible physical process where matter changes from one form to another due to the addition or removal of heat energy. I am going to draw two diagrams here to explain what I mean by change of states. Let's suppose that this is a triangle. For the sake of this video, I want to use eyes as a case study matter to explain change of states. So let's say this is our eyes, and so let's call this tip solid eyes. Solid. Let's call this liquid. Let's call this gas, or let's say steam. I believe you know that we have 4 states of matter. We have solid, liquid, gas, and plasma. We are not looking at plasma in this video, so let's stop at this level. Now, arrow down, we talk of what? Arrow down is change of state from solid to liquid. We call it fusion. So we write fusion here. It is called fusion or melting. So arrow up is the change of state from liquid to solid due to removal of heat energy. Change of state from solid to liquid due to addition of heat energy is called fusion. So we say that fusion is a physical process whereby matter changes from solid to liquid due to the addition of heat energy. Here we say freezing. Freezing or solidification. When you remove heat energy out of matter, out of this system, it will freeze, it will go back to this stage, solid state. And that was the reason why I said change of state is a reversible physical process. Now, if you continue to add heat energy into the system, matter will, the liquid ice will now vaporize into what we call gas. I will call this process vaporization. Vaporization. Now, if you decide to remove heat energy at this stage, this guy will reverse back to liquid. We call it condensation. So you see that it is forward-backward reaction. And then there are some substances that changes from solid straight to gas, and from gas straight to liquid. You can make research on that and know the substance. But for the sake of this video, we are looking at 1, 2. We are not considering this wing. I will stop there. I also want to draw another diagram to explain this topic very well. I call this diagram the heating curve for solid ice. So let's draw a diagram called the heating curve for solid ice. The heating curve for solid ice. Yes. So follow me steadily. So this is my theta in degrees Celsius, and this is my quantity of heat energy in joules. Stay with me as I explain this. Now, there is a particular heat that is responsible for this change of state. That is why I have put this topic as change of state and latent heat. Latent heat is actually the heat energy that is responsible for every change of state. Do you understand? It is an invisible heat, a heat that comes with a constant temperature, with no change in temperature. So what do we mean by latent heat? Latent heat is defined as the quantity of heat energy that is required to change the entire mass of a substance from one state to another due to the addition or removal of heat energy without a change in temperature. In simple terms, latent heat is defined as the quantity of heat energy that is required to change the entire mass of the substance from one state to another state of matter without a change in temperature. I hope that is well understood. Now, we said that latent heat is responsible for changing of matter from one state to another without a change in temperature. The heat responsible to change solid to liquid is called latent heat of fusion. The heat responsible to change liquid to gaseous state or steam is called latent heat of vaporization. Now there's what we call specific latent heat. Specific latent heat is defined as the quantity of heat energy that is required to change the unit mass of a substance from one form to another form without a change in temperature. Without a change in temperature is an operational term that, if not included in your definition, you will be marked down. Now, specific latent heat of fusion. Specific latent heat of fusion is the quantity of heat energy that is required to change a unit mass of a substance from solid to liquid without a change in temperature. Specific latent heat of vaporization is a quantity of heat energy that is required to change a unit mass of a substance from liquid to gaseous state at boiling point without a change in temperature. Now, if I decide to draw something like this, please stay with me. From this point to this point. So I call this is my 0 degrees Celsius. And down here is my minus, before I put in the values. So this is my -2, -4, -6, -8, -10, -12, -14, -16. Now, this is the quantity of heat energy in joules. This is the quantity of heat energy. In joules. So let's say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 joules of energy. Now, this solid ice, it will interest you to know that water freezes at 0 degrees. And at that same 0 degrees, we also have liquid water. So at 0 degrees, you have a mixture of ice and liquid. So, this point, we call this the melting point. Melting what? Melting point. So water melts at 0 degrees and water also freezes at the same what? 0 degrees Celsius. Now, let me draw something like this again. And then another arrow up again. This is 1, 2, 3, 4. 1, 2, 3, 4. Another arrow here. And then another arrow here. And then another one here. Good. So let's call these points. This is point A. This is point B. This is point C. This is point D. This is point E. And this is point F. A, B, C, D, E, F. Please stay with me. I am about to explain something very, very important. Now, anything from 0 degrees down is ice. Water freezes at 0 degrees. So, anything 0 degrees down, we have ice. -2, -4, -5. In fact, let me say -infinity degrees Celsius. This is where we have what's called dried ice. -1000, -3000, we have dry ice. As you can see in the movie Fast and Furious. Fast and Furious is a movie where you see those guys driving their heavyweight cars on ice. That can only happen when that ice is a dried ice. The ice that looks like a mountain, very solid, very dense, very strong. 0 degrees down to -1000, -5000, that is where you have what's called dry ice. So anything ice is from 0 degrees down. Now, when you continue to add heat energy, at this point here, is a point where heat energy was not added into the system. Let's say this is 0 joules. At this point, heat energy was not added into the system. So the moment you introduce heat energy into the system, the temperature of this ice will start rising. will start rising up. And at this point B, you have a mixture of ice and liquid. If you continue to add heat energy, you have what's called fusion now. A process where matter will start, the ice will start changing from what? Solid, from solid to liquid. So from point A to B, you have solid ice. You have solid. At point B, down to somewhere half here, you have a mixture of ice and liquid. At point C, you have what's called total liquid. So let's write. This is solid. This is liquid. This is liquid. This is gas. Gas or steam. Solid, liquid, gas. Solid, liquid, gas. Solid, liquid, gas. Solid, liquid, gas. So, addition of heat energy to change from A to B, you have solid here. So from B to C is what? Fusion. So we call this fusion process or melting process. So that's why we call this point melting point. B to C is melting, where the ice melts from solid to liquid. At C it is pure water. And so at this point the temperature is constant. So let's write melting. Melting process, also known as fusion. Now, from here to here is heating process. From here to here is also heating process, but also melting process. And then from here to here, you have from C to D, you have what is called boiling water. From B to C, the temperature is constant. The temperature will start rising again from C to D, and we'll jump this what is called boiling point. Right. This is when we call it the boiling point. At boiling point, you have 100 degrees Celsius. So we call this boiling. Right. Boiling. Boiling point. This is the boiling point. At boiling point, the temperature of the water or the liquid is still constant. So from D to E, you have water, you have liquid that is very, very hot. If you continue to add heat energy to the system, this liquid will change at point D, we change from point E to E as steam or gas. Now let me include the equations that are responsible for each of these processes. From point A to B, recall that the quantity of heat energy that is required to raise the temperature of a substance or unit mass was given in the other video as well. H is equals to mc change in theta. You also had H is equals to what? Cp change in theta. So the latent heat is defined, the specific latent heat of fusion and vaporization are defined as follows. From the equation H is equals to ml Fi, we call this latent heat of fusion. The Lf is called latent heat of fusion. So if you make this guy the subject of the formula, you have your Lf is equals to H over mass. So the latent heat of fusion is given as joule per kilogram. That is the equation. The latent heat of vaporization is given as H is equals to mLV. So you say that your LV is equals to H over what? Mass. Still the unit of what? Joule per kilogram. Now, I told you that from here to here, the equation you have is this. So write that HAB HAB is equal to what? Mass of the ice times specific equals to the ice times what? Change in temperature. Here you have latent heat of fusion. So you pick this equation. This is what you have here. Latent heat of fusion. This is what you have. So here you have what? The heat responsible for this guy here is given as what? HBC. HBC is given as what? Mass of what? Mass of ice, or let's say mass of, yes, mass of ice, because here you still have mixture of ice and liquid. So mass of ice times latent heat of fusion of what? Of ice. HBC is equal to mass of ice times latent heat of fusion of ice. From C to D, this is the equation that you have. You have HCD is equal to what? And from C to D, it is purely liquid. So it's a mass of liquid times specific quantity of liquid times change in temperature. From D to E, it is vaporization. We call it what? Vaporization process. And the heat energy responsible to vaporize this liquid from this substance from liquid to gas is given as H is equal to what? Is equal to mass of liquid times latent heat of vaporization of what? Liquid. That's it. So we call it, sorry, this HDE. HDE. Yes, HDE is that. So from here to here, the change in temperature from this point to this point is given as a change in theta is equals to. There are moments that you have some substance that their boiling point is less than 100 degrees Celsius, or some that are above 100 degrees Celsius. As the case may be, the change in temperature here, let's use 100 as a case study. You may have less than that, but let's say change in temperature is 100 degrees minus 0. That is the change in temperature from this point down to this particular point. From the boiling point down to the melting point, the change in temperature is given as 100 minus 0 degrees. Then the change in heat energy from 0 down to minus whatever, the change in temperature here is given as what? Let's use minus 12 as a case study. We can say that maybe minus 12, we can say that what? 0 minus what? 12. 0 minus 12. Mind you, 0 is greater than any number down here. So 0 minus 2, 0 minus 4, 0 minus 15 becomes the change in temperature. So if you come back here, you're going to write as your HAB is equal to mass of ice times specific quantity of ice into what? 0 minus, let's say 12. We are using 12 as a case study here. If you come up here, there's no temperature because at melting or melting point, the temperature is constant. That is why you don't have temperature here. Back here, you may write that your HCD is equals to mass of liquid times specific quantity of liquid times change in temperature, which is 100, in this case 100 minus 0 degrees. It could be 90 minus 0 degrees, or 80 minus 0 degrees, or 5 minus 0 degrees, as the case may be. Then up here again, you will have this as our boiling point. The heat responsible to change this liquid from D to E into vapor, from E to F, is called the specific latent heat of vaporization. And so this is it. So at point DE, you have specific latent heat of vaporization. At point BC, you have specific latent heat of fusion. At point AB, you have just normal heat energy that can change or increase the temperature of the system. And then from point CD and also DE, you have the heat energy that is responsible to change it from maybe a gas to maybe plasma. That's it. So now, before I conclude on this video, there are some questions that are asked this way. Calculate the total quantity of heat energy that is required to raise the temperature of so and so kilogram of mass from minus 14 degrees to steam. That is, we evaporate it completely and leave the container empty. You place ice inside a container at minus something degrees, and they are asking you to calculate the quantity of heat energy that will be required to heat this guy, melt the ice, change it from solid to liquid, from liquid to gaseous state, and evaporate it completely. As simple as you can see on the board. What will you write? The total quantity of heat energy that can do this work, the total quantity of heat energy that can do this work, HT, is given as what? HAB, which is this guy, plus what? HBC, which is this guy, which is this equation, plus what? HCD plus HCD, plus what? HDE. So you have 1, 2, 3, 4. 4 different forms of energy that can evaporate dry ice at this point to steam at F. So you have 1, 2, 3, 4. This will vaporize it from liquid to gaseous state completely, and then will leave you with an empty container. To this, we have come to the end of this video. So if you want to write in summary, you can say that your H total is equal to what? Mass of ice, specific quantity of ice into change in temperature plus MIL VI plus mass of liquid, this of liquid, change in temperature plus what? M of liquid, LV of liquid. So this is the total quantity of heat energy that will be required to change dry ice from A to steam. We call this diagram the heating curve for solid ice. It will interest you to know that going this way is heating curve. Is what? Addition of heat energy. And coming this way is what? Removal of heat energy. This step down is removal of heat energy. Going up is addition of heat energy. What I'm trying to say is that coming down is cooling curve. Going up is heating curve. See you in the next video, where we shall look at a lot of calculations on this topic. God bless you. Subscribe to my channel and share. Bye-bye.